We'll see what happens. Oh, only an hour and a half left. I don't know. We'll do whatever it takes for this one. I don't have another place to be. How's everybody doing? All right. I should have brought a sign-in sheet. This thing you can check. Can we circulate a piece of paper? Just for records. It's not like if you weren't here, anything against it.
I just have to go at like 2:50.
You know what? I'm okay with that.
Thank you so much.
So we're going to say, you know, you should just go now.
I know, I'm trying to like make it kind of. What's he about to say? I don't know. I don't plan to say that. Oh.
You see your name and then Professor.
What's the best way to use this? What if I would document recovery? That's bad. That's not bad. Back. Well, that might be a little better.
Don't these ones up. Welcome. We're happy to have you.
Would you like that? We don't have to worry about this. We'll just use the board.
Are we go?
Thanks, you. It's almost like ARICO. This is getting recorded, by the way, so she could be angry at me now for turning her name into a bingo. So. All right, so what do you want to work on? Let's see. You know what we usually do? We usually talk about the equation sheet. I don't want to waste too much time talking about the equation sheet, but that's our go-to thing. You can barely read that, but you have your equation sheet somewhere in here. And in looking at this, do I also? I can't tell. Do I have Newton's second law as part of that? I think this is a one from last year. I can't read this. I don't want to mess around with it. Anyway, I want to make sure that so I think actually I need to be stretching it up onto there. Because we also want to have Newton's second law. Because last year the Newton's second law was not included onto the. Whoops. I'm messing that up. Oh man, you're screwing me up. Go stop it. Okay, there you go. Oh, you're making me seasick. Okay. N2L, work energy, and impulse momentum. And we also have power and efficiency. Those are the topics on exam 2. And we have a lot of things carrying over from kinematics as well. So that's unfortunately this, or fortunately, I don't know. Every topic builds upon the other topics. So we can't just purge right after every exam. You could wait till summer to purge. And you can just let it go away. Never think of dynamics ever again. No, that's not true. So what would you like to work on? I can sorry.
Can we give an example of each, like how to find
Sure, absolutely. Do you happen to know one in particular that you want to turn in? I like to pick Newton's second law one right here. Wait, is that one that I have as part of this? Let's see that. Yes. Is that one of my problems? Don't look familiar.
See a little panic attack here. Where the hell is that going?
Oh, that's why I took the lid off. It bothered me.
Yes.
It's also
Let me see.
I'm like, sorry, so long.
That's interesting. Where did that come from? That's crazy. Oh, sorry. Go over that. Genetics, rectangular coordination.
So, oh, I see. There it is. Okay. We have many things going on here. We have kinetics. We have constrained motion. So this block is initially at rest, and then we let go of it. And apparently it's enough to make the thing move. Or let's screw this whole thing up right here. So not very good resolution. The coefficient of static friction is 0.25. Let's just go ahead and assume it's moving, right? We don't, but we could do the thing where we'd have to do statics to start with and see, hey, does it start sliding? Because the static friction could be sufficient so the thing doesn't move at all. But why would we ask you that question? That would just be a trick, right? Because it's dynamics, so it should be moving. So let's just all agree. We all okay with that?
Yep.
Okay, so forget about that. The kinetic friction is 0.2. Coefficient of friction. Mass A is equal to, let's see, 10 kilograms. So MA is 10 kilograms. And the angle is 30 degrees. I'll put that over here. 30 degrees. They tell us what the mass, okay, that does later on. The minimum mass block B that causes it to move downwards. Okay, so I just lied a second ago, and we actually do need to use statics. All right, so let's start out and see what has to happen right here. We could draw our free body diagrams and our inertial body diagrams to start with, and to only use the free body diagram portion of it for part A. So let's, we have to do them separately. So do an FBD and an IBD. I'll keep them relatively small so I can use the space because I want to be able to see them there. I don't know if they're going to be able to read my text. Well, we'll just see. We'll do the best we can. All right. In this one, we have a force coming up here, and we'll rotate. This is the X. I'll call this X prime and Y prime. I like to do that, and it's going to equal to the box over here, right? And we'll put in our normal force, Fn, and our friction force, F, and this is going to be our tension in there. And don't forget the weight. And this I'll call it mg instead of giving it in. And I don't, we're not going to need this for the first part, the IBD part, but we will going to need it for the second. We want to find out we don't quite know which way it's going to move. Is it going to move this away or this away? First off, we're saying so the minimum mass of block B that causes it to move downwards. Okay. So I'm going to guess, I don't know 100% sure until I get the solution to part A, whether block A is moving down the slope or up the slope.
Unless they're talking about block B moving downwards.
Yeah. That's the wording of the thing is kind of messed up. Well, so we don't know. I mean, block B could be less than this right here, but let's make it, for now, let's just say that it's going positive, right there, right? We'll assume that the thing is going positive, and we'll figure the thing out from there. And so that's going to be MA. It turns out that it's actually going the other direction. So the minimum mass for block B that causes block B to move downwards. See, that's the phrasing of the thing that messes me up. Causes it must mean block B, not causing block A to move downwards. In the solution, this ends up being in the opposite direction. Let's see what happens. So we'll do the other FBD and IBD right here of this. I'm going to run out of space if this is all I'm going to use, but it's okay. And so I have, for block B, we have, let's include the pulley right here so that we can have these forces so that they'll do the same thing. Otherwise, we could just write 2 times FT, but I will do it this way here. FT and FT, and we have, this should be mass A over here. So this mass B, G, staying alive. Okay. And the way I've drawn it right here, if we're going to guess a direction, make sure you're always guessing consistently. Right? That's the thing that will mess you up in the end, is if you guess one way here and you guess one way over here, you get all kinds of messed up the thing. But you can guess. So we know that if it is going this way, that block B will end up coming down here. So this is the acceleration of B. We want to make sure, okay, so for our statics portion of the thing, and I'm not going to have enough space, I'll say the sum of the forces in the y I guess I have to do this twice here. Sum of the forces in the y direction, y prime direction, right here, for this guy right here is going to be, and so this is 30 degrees here, 30 degrees there, 30 degrees there. So this right here is going to be 30 degrees, I believe. Is that true? I drew this like too much like it's 45 degrees. Okay. Yeah, okay. I convinced myself. And so we're going to have mass A, gravity, and that's going to be the cosine of 30 degrees. Do that correctly? Sure. And it's going to be negative there, and that's going to be F. Oh. And plus Fn is equal to 0. So Fn is equal to MAG, a little bigger, cosine of 30 degrees. And so that ends up being, where'd you go? Where'd you go? We don't solve for an in-between number in my solution here. So what we end up having is the friction force, therefore, is going to be, I'll leave it without a subscript because we want to use the same thing again for the dynamics part of it. And we'll just say that it's going to be times Fn, so that's going to be mu MAG cosine of 30 degrees. So now we could go and using this, we could go for the statics of this and set the thing up and say that it's going to be the sum of the forces in the x prime direction is going to be equal to 0 in our first quest right here. We're going to try to figure it because we're going to solve for what MB needs to be for this thing to move. And so in that case, for when we get to mu, we're going to use them as the 0.25 because that's for the part A, for the statics part. And systematically breaking the thing down, we say that Ft, that's positive in the x prime direction, and it's going to have like a minus MAG. We have a component here times the sine of theta, and then it's going to be, Well, you know what? I need to be consistent, so I made a mistake here. I have to draw this guy right here. If I'm making the motion that way, the friction force has to be this way, right? Got to be careful with that. So I caught my own mistake. It's important to try to catch your own mistakes as you're working through something. So that's going to be the negative. Okay. So we'll write, this is going to be mu ma g cosine. It's going to be equal to 0. Later, this is going to be equal to the mass times the acceleration. Then we can do the same thing over here. Get the sum of the forces in the y direction, positive being right here. I should have done something over there that would be consistent. And we're going to write that 2ft minus mvg is equal to 0. So we'll say that it's going to be ft has to be equal to 1/2 mvg. And then we plug that back into over here. So 1/2 mvg minus mag sine of theta minus mu mag cosine of theta all have to equal 0. And we plug some numbers in and we get what the mass of B has to be. And did they ever solve for that? I don't think they did part. I don't think I have an answer, numeric answer for that in the solution here. And I don't know why. I'm going to write the whole thing out here, right? 2 times, what's MA? Is MA 10? Yeah. So you got 10, 9.81, got a lot of 9.81s in there. In fact, I think actually all the G's cancel out. We could actually save ourselves a little bit of time here by canceling a couple things out here. We got G's cancel each other out. That's kind of surprising, isn't it? So we end up with M, and there's going to be an MA over here that's going to come out of the thing. So this ends up being sine of theta plus mu times cosine of theta. And that whole thing times 2, right? So if you wanted to get an answer to the thing, I don't know if my calculator here. Anybody playing the home version of the game? 30, get the cosine of that. I see a cosh. No, I don't want the cosh. Multiply it by r. I could have put the values in there, couldn't I? Mu is 0.25. 0.25 equals, and then I want to have plus sine of 30. Is this going to work? Right? And I think it was then times 10 equals, and then times 2 equals. So it's 14.33 is what I end up getting. Anybody else agree with that? Or does anybody, you're just here for that's kilograms. I was about to write pounds. And once again, I don't know why, but whoever wrote the solution of this, because this isn't my handwriting, didn't bother to answer that part of the question. For the dynamics part now, so that was part A. For part B, they say the mass of the block is 25 kilograms. And am I correct in saying that this if that's true, then it has to be moving downwards, so this has to be the correct thing, right? I think so. Some maniac threw it the other way. I don't know who this person is. Maybe just slap them around somewhere. Oh, no, okay, the final answer, I don't know why. I guess maybe they were trying to demonstrate something. Maybe they were having a moment of losing their mind. They also decided that positive was down this way. You can't trust people, right? I don't know. People will let you down. That's a wonderful attitude to have. No, sorry. Mr. Positivity will come out one of these days. But we could reuse most everything that we have up here and get rid of that. So for the dynamics part of the thing, I would not have asked part A on an exam. But we want to get dependent motion. Might have been the first thing I would have tried on this. I might want to get that out of the way. It's because everybody loves dependent motion so much. There's books don't even ask this. Some dynamics but don't even include this type of thing in there. I don't think Tong did. Did they? Yeah. When you took it, yeah. It's like a Beer Johnson session. They just really I guess maybe they worked on an old timey ship and had lots of pulleys and things. I don't know. So we go YB, and this is the one we use. It's a simple enough thing that we could have as part of this, right? That we could do this kind of in our head. But it's good to be systematic. So we have the length of that rope is going to be XA plus 2YB. So the velocity relationship between them is going to be VA plus 2VB, and the acceleration relationship is going to be here. And I get a little nervous about playing the sign convention thing with some of these pulleys. This will work out, but and some of them, they can be kind of messed up because you decided that positive was this direction, and that doesn't make any sense that positive would be that direction. So most of the time, I will just say absolute value right there, and that. I just know the magnitudes. I can tell which way the things are going to move, and I'm not going to play whether things are positive or negative as part of that. That's something I would have gotten out of the way. I'd rewrite this thing out. The sum of the forces in the x prime direction are going to be equal to mass times acceleration in the x prime direction. X prime being that direction right here. So I could have saved myself some more time by just erasing a little bit of the thing, but I didn't think that was fair because you wouldn't be doing that yourself, right? I'd be cheating you out of a little bit of information here. So once again, we say our FT minus G times the sine of theta and minus our mu. This time it's going to be a different value of mu times not Fn. This one. MAG cosine of 30 degrees. I guess I could put 30 in there too. Generic. I think I got everything I need, and that's going to be MA and then X. AA. Oof. Boy, that's really flustered. Okay, and then over here we do this thing again and say the sum of the forces in the y direction equals mass times acceleration in the y direction, and declare all those things, and then say that we have 2 FT minus MVG, staying alive, and then minus, we have to be careful with our signs right here, MV, AB as part of that. And now we have 2 equations here, and the things we don't know are FT, AA, and AB. So we have 3 unknowns, 2 equations. Our third equation. We're able to solve the thing, right? And the rest is just putting numbers into it. You're totally capable of doing that. And when we get done with the answer to the thing, in the solution that you will eventually see when it gets posted, I think it'll be Sunday night that I'll post the thing. Just to get you, I want to get you like not tempted over the weekend. And exam 3, I'll put it even like it'll be even sooner, trying to get you to. You'll have that self-discipline. I know some people you probably already have it. There's just some people. The reason why I do this, if I could, I won't be able to convince everyone. I know, but I try. I feel like I should. That I'm not being just a jerk about it. But I really want to save you from yourselves. There will be a certain number of people that will just read the solutions, and I just want to try to get maybe that one person that because I haven't posted the solution will actually like work through a problem sooner instead of just reading it. Maybe I could stop one person from failing, and I'll have accomplished something. But anyway, you'll see the numeric answer to the thing if we haven't already. I think I do have it somewhere. Yeah, I put it up there. It's 3.48 going upwards. You can see in the quadrant. Remember, this has to be the answer needs to be with a direction, right? And to be a vector, you need to have the correct units, which this one doesn't. So marks off to me. And this was Valentine. Look at Jim. Nice. And then it needs to have a quadrant. This one, maybe we could say, it's in the, what do they call it, the first quadrant over there, upper right one? I never know, but it's my good best way now. But you could see that, like, we picked the right direction. If we ended up with negative numbers, we would see, like, okay. Our alarm bells would go off, and then, we would want to, that negative would also make us, like, question if maybe we hadn't made a math mistake, too. So we were trying to triple check. But you wouldn't want to do that immediately if this was the first problem on the exam. Or maybe make a little mark to yourself, a little note to yourself to come back to it. I get so frustrated by people not finishing exams or not leaving an exam problem blank. They're very easy to grade, but it's very upsetting to me to see someone not succeed because they haven't managed their time well. So that's a Newton's second law. Let's do a work energy, as we were asked to do one of each, right? Try it. Oh, I could go for some more coffee. Let's see. One thing as part of the Newton's second law that you want to double, triple check is that it was broken into 3 different categories, 3 different kinds. Really, we only had 2 classes on it this semester. Other semesters I would have had 3 classes. So we broke up the path and the polar so that we would have Newton's second law in rectangular, Newton's second law with path coordinates, and Newton's second law in polar coordinates. So those are 3 different kinds of problems that you should become familiar with and be able to do, right? And there could be some variation in there that, one I don't think that we did that often happens in the path, is to have like a car or something on a bank, right? So the actual path coordinates thing is actually going around looking at the vertical, from above, right? So that we have an acceleration that's going towards the center. But then a lot of times we will do it looking at this way right here, where we're going to have, let me draw it correctly right here. I don't know if I have one of these in my practice problems. I'm not sure we did one as a homework problem, but it is one. I know it seems like it's unfair. We didn't do this kind of problem. You will say those kinds of things, and you will be incorrect. It is fair. That's what we're trying to get you to solve the new problem by applying a concept, right? So just because you weren't asked something, but I would warn you just that like you could be asked for something like this, where the acceleration is mass times the acceleration, but that's going to be the normal acceleration, right? Because the normal acceleration is pointing to the center of the thing, and in this view right here. So we have a weight going right here, and a lot of times we treat these as particles, so there's really we'll just draw one force in the normal direction, but we could have a friction force coming up right here. Does that make sense? That you could be asked something like that? Because that is an application of the normal, the path FEA, not FEA, the path N2L, Newton's second law. I have other ones in there where there's like a ball on a string. There's like, here's one where we also have one where there's kids on a swing type of problem. So here's the ball on a string kind of problem. Here is the kids on a swing, and so now they have like an angle. So now when you have the kid right here, you might want to have like some kind of angle coming up right here. So you have an FBD and an IBD, and they equal to each other. And so now that you have like, here the MAN coming this way right here, but you have a tangent, and you have a weight actually right there. Does that make sense? You could have that kind of problem. Right. And it's a little difficult to ask the polar ones, I guess not too difficult. It's actually a little easier when they're rigid body motion to actually ask the polar ones. For a particle, it gets sometimes the arrangement can get kind of messy. To try to get that, to figure out a way to get an R dot and R double dots and a theta dot and a theta double dot as part of it. So this is a work energy one. It's pretty simple though, with the springs. I like the kitchen sink ones. I really kind of like, and then this is evil, I really kind of like the ones where we combine different things, like combine impulse or impact and then work energy and that kind of thing. I'm always looking to try to write one that isn't too difficult, but is challenging enough to be able to try to measure your ability to solve the problem. That's really what the exam is there for, so I try to keep it to the spirit of that. So here is one that kind of does that. So this is a challenging one right here, where we have boy, that's really hard to read for you, isn't it? Damn. Is there a way to it's perfectly fine on the screen here. It's the focus is not good. And I don't think there's any way to remotely do that. Could we make it darker somehow? Maybe, what I could do is I could click on this, and go to Format and Corrections. Makes it a little better, do you think? You can't quite see this, right? So
it looks fine on the screen. So I think it's just to focus.
Oh yeah, it's because it's that far away for the thing. Yeah, that's a breakdown in this room, right? Damn. Can't have it both ways. Can't. So always something. Thank you. That's the case. So we got a ball right here, and it's initially traveling at 2 meters per second, and it weighs 75 grams, which isn't a lot. And so it comes down and makes an arc right here, boom, and then it comes back up, and we happen to know it's 0.6 meters that it gets to right there, and it's bouncing off of a thing that's 400 grams, and it's got springs, and I don't think they bottom out. And let's see, knowing that the height of the rebound is 0.6, right? And by the way, I didn't draw this the 100% correct way. This comes up here, and that's the height, that's its zenith, if you will, after the bounce. So that's an important thing to know, that it gets there. So what's special about right here? Yeah, it's a zero velocity. So what does that mean about energy? It's all potential energy now, right? All the kinetic energy went away. out of the thing. Well, all the kinetic energy that we're going to care about. Let me think if I could think about that. Yeah, this is an impulse and momentum problem, not a potential energy problem. So I have to be careful what I said about that because it does have X. But that's okay because it'll cancel. It was constant, so the kinetic, that part of the kinetic energy is going to cancel each other out. So, but let's not worry about that. So this is an impulse and momentum problem. I just noticed that. I don't know why my slides put it right there. And it says you must use there. So 7, okay, is projected at a height of 1.6. So there's 1.6 meters right here. And bounces, rebound, 6 meters. We want to find the velocity of the plate immediately after impact. We want to find the coefficient of restitution between the ball and the plate. So what we can end up doing is finding what the velocity of the ball just before and just after, right? So just before it hits the velocity of the ball, and then we can find the velocity of the ball just after it hits. And we notice because it doesn't return back to the same place that it loses. There's an inefficiency there. So I might ask that right there because it's an impulse and momentum problem, but then you have to use kind of like the kinetic energy of the thing, kind of think your way through, and there's efficiency. So there's that. Oh man, yeah, good stuff. So anyway, we'll figure out the velocity of the ball. I guess I want to write. I guess I got to give him a name. I'll call him A, and I'll call him B. Whoever solved this right here, I know who it was. Didn't bother to do that. And I don't like capital V. I go V A right here. And maybe we'll number these sequences right here. We'll say that this is, let's call that 0. Let's call this 1. We'll call it 2 after the fact, and we'll call this 3. Give it numbers. VA1, one right here, is going to be equal to that squared VA0 squared minus 2G, and then I guess we'll go delta Y 1, 2. Triangle. And then so we take a look at this, and this is in the Y direction, I should point out. Yeah, because it was horizontal right there. I don't know if we need that. Do we need the thing in the? Yes, maybe. I don't think we ever need the tangential in the X direction. If we could ask what the angle is. If we ask what the angle is right here, that's just being a jerk about the thing. But no, it's not too bad. I don't know. Something. We use it for something. So this is 0 right here. That's my point, and I recognize, I better make sure that it's in the Y direction. That we're going to end up and find that this one right here in the Y direction was going to be equal to the square root of 2, 9.81. I better keep that negative in there. Oh no, negative. It's complex. No. But delta Y right here was in the negative direction. It would have been like starting out at 1.6. So it would have been 0 minus 1.6 right there. So that's where the minus would have gone right onto the thing. And 3.431 meters per second. And we could do this thing, I just skipped a line right here. That's, for this guy right here, this was the 5.603 meters per second. And we could say that we would notice that all these same things would end up actually being true for over here, right? So let me write it out. We could say that VA3 y squared is going to be equal to VA2 y squared minus G 2G, excuse me. And that would be delta y from 2 to 3, right? So this is actually going to be 0 here, and it's going to be equal to the VA2 y squared minus 2, 9.81, and this one is going to be, once again, I think 0.6, yes, and minus 0. Okay, yeah, it's stuck right there. Okay, so then that gets rid of this right here, and we're able to find VA2, and I said 2? Yes, 2, yes. Y is going to be equal to 3.431. They skipped all of this in the solution, and they just said, they recognized what the form was, and they just plugged the other number in. So if you read that, don't be too confused. I think it's better to be a little bit more methodical, but if you wanted to save some time. Then we could say that we could ask the answer. Let's see, the velocity of the plate immediately after the impact. So what we have is it's a good practice, and they didn't do it here, to have our before impulse. I usually write initial, don't I? Initial. Okay. Initial and then final. It was 3. So we have this, kaboom, equals this, which we happen to know what directions these things are going. So this is going to be our MAVA1, right? In the way that we numbered it, sure. And then this is going to be MAVA2, and then presumably MBVB2, right? And so shoving some numbers in here, because these were given in grams, we could go, and they're going to cancel each other out. We don't have to turn them into kilograms. But if we got to be careful with the units, you can go, they all cancel each other out, so we're fine here. But just be aware that, like, if we ask for like a force as part of this, you should turn it into kilograms, right? It's so funny. He's laughing. What's going on?
You just let me know until.
What's that?
You're just letting me know until. What this like.
Okay, cool. I just want to be on this joke. I don't know. I'm flying. Okay. So, oh, by the way, we want to, anytime we do this, we want to establish positive and negative, right? So, as part of this diagram here, that's an important part, because impulse and momentum are vectors. So we have positive and negative things going on. So we can say that this is negative momentum, or we can say that it's going to be negative velocity here of 5.603 right here. These are equal and opposite. And I know that probably many professors just leave it out because, or they might not even draw this diagram. I think the diagram helps you think your way through the thing and try to convince yourself. But maybe the problem is straightforward as this, and repetitive is a conservation of momentum. Maybe you don't need to do it. But it's the other problems when it does become a thing that you want to try to catch. So I think it's just good to be maybe a little consistent and try to just to convince yourself that you're taking things into account. And so now we're going to have a positive 75 times the velocity, the second one that we got, the 3.431, and now it's going to have a plus the 400, and we don't know this velocity, but let's put a negative right there. I mean, we could have assumed this was in the positive direction, but it's kind of obvious it's going to go down. So we would find the thing. And then if we put those two things into each other, we know it's going to be a fairly small number, but I guess it isn't that small. 70, whatever. 1.694 meters per second. And if they ask for a velocity, this is not a complete answer until it's a vector. And it ain't a vector until it has an arrow. And now we want, yes sir?
I was going to ask, is everybody clear why the impulse term is 0? So it's like fairly typical in these types of problems. Newton's third law, equal opposite forces.
Yeah. They cancel each other out. It's internal to each other. Yeah. They're going to rebound. And that also is going to be equal and opposite. And it's a process, right? They're not. This actually, if you were to get a high-speed camera, you can watch the thing crush, right? And the strain energy gets, and so it's a process where that force is not constant. It actually acts. It happens over time. You ever watch the golf? You ever like they do the zoom in on the golf ball getting hit? I love that. I wish I could, you can actually kind of feel it when it happens, right? And when you actually get that good compression going on, oh. But then most of the time I'm shanking it into the freaking woods. My golf life. Shouldn't complain. I love complaining. Just terrible. What does it say underneath there? Oh, we want the coefficient of restitution. So that is equal to, we can look up the equation, or you could just memorize this, right? That is going to be the negative rel vel after divided by the rel vel before. And you could do either one first. Just make sure you do an opposite on the bottom, right? So you could go like VA2 minus VB2 divided by VB1 minus VA1. Doesn't matter which one you go, but as long as you get them backwards. Because that's where the minus is happening right here. So A2 ended up being 5 point, it became right above it. Remember? 3 should be nicer to yourself. There. And you go minus. Now you got to be careful with the minuses, the signs right here. Okay? So did I do that correctly? Yes. Right? Because this one is going upwards. This one is going downwards. This one is going downwards. So we want to keep track of that right there. So this could be minus, but this one's going to be minus as well. Did I get that right? Am I correct in that? I'm getting nervous. So this right here, right? But now I'm wondering about the other guy. Oh, I see. It's going to be nice. Okay, good. 1694 divided by 0 minus 5.603. And if we did everything correctly, we get 0.914. If we did it incorrectly, it would be greater than 1. Or it would be negative, right? So those are indications that it's a poorly written problem or you made a mistake somewhere. So be on the lookout. Those kinds of things are actually good checks for yourself, right? But once again, if you did get that thing messed up, don't spend another half hour trying to find that mistake. Go to the next problem, please. Okay. Any questions on that? That's a good problem. I don't know how it got. Well, I guess this was part. Okay, I didn't organize them that way. I see what happened. I know why. I thought it was like on the last page or something. Let's get another. Can I erase? Or are we still? You got any requests there? We're going to go to work energy, and then we can go to take some more requests. I think we have the big three out of the way. You can be asked impulse momentum problems that are not impact problems, by the way. Just to be clear on that, because that is a particular subcategory of the thing. So let me see here. There's a work energy right here on a sliding thing. Method, coefficient restitution, I guess, there's not a kitchen sink problem. I like the kitchen sink problems, but they're a little mean. You know what I mean by the kitchen sink? What I would mean by a kitchen sink problem on this thing? There's like absolutely everything going on that could possibly happen, right? So we have maybe external force, could be friction. We could have friction and an external force being placed onto the thing. Like I have made problems like that before, where we had a box attached to a pulley system right here, and we have somebody pushing a force onto the thing, and maybe there's a spring happening right there, and there's some kind of friction going on, and it has an initial velocity, and then you want to find the final velocity, or some mean thing like that. So you have to do every single one of them. But here we have two 20 kilogram block. So this is 20 kilograms right here. And it's at rest. It's released from rest and it slides down the slope. Okay. So, and this was the 10 kilogram. And then we're about to sneeze. Only two. My wife can sneeze like almost like a machine gun. Choo, 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 choo. Like this right here. It says, I'll say it for posterity too. It's getting recorded here. So but they used to, when she was like in grade school, all the students would start counting because she could do like 10 in a row. And she's very polite, so sometimes she tries to hold the sneeze in. You know how much that seems like dangerous to me? Like your head's going to explode. It's kind of fun to watch. I'm amusing. All right, so we got the coefficient of friction in between here is, and that's kinetic because we are not going to make you do a statics problem in the beginning. It's a waste of time. And you do not need to demonstrate that it moves. That was nice of you to tell us. And we want to find the velocity of block B after A has moved down the slope 2 meters. That's a little difficult, so you have to be careful at the phrasing of it. I think they mean in that direction instead of that direction. That would be kind of evil to have said here. So I think that's what they mean, is that amount of position of being 2 meters. And that means that this thing is moving up, and it doesn't look like there's enough room for it to move up, but that's okay. We'll pretend. Let's pretend. So this is going up 2 meters as well. The best way to approach any of these problems is to write out the big equation. KE1 plus PE1 plus any work that's external that happening onto the thing is equal to KE2 E2 plus PE2. Write that out and then start trying to populate it, trying to figure the thing out. In fact, what I like to do is make a list of them, right? So I start out and I start thinking my through. KE1 is equal to what? That's true, but in this case, it's not moving. It's released from rest, right? So 0. Yay. Okay. And then PE2. So now we get to this on the PE1. Excuse me. We get to this, and we have to start thinking our way through. Like, okay, how are we going to approach this? So we might actually recognize this ahead of time, but right here might be the spot where we go, oh wait, this one's moving up and that one's moving down. How am I gonna work this out? What do you think you need to do?
Looks like a triangle to me with the angle, and you have the 2 meters in there. That's kind of a triangle there between that and that block.
I'm thinking what I was aiming for here is you need to establish some datums, right? So I want to try to figure out, all right, well, what is my reference when I'm talking about potential energy? I need to have something in mind that I'm saying, okay, what am I going to consider to be 0? Well, in this particular problem, because we have 2 different pieces in there, we can have 2 different datums, right? So each one is going to have its own datum, and so we don't need to have a global datum. We could just as easily, if we wanted to, make a single datum that was down here. So really, I don't like negative potential energy. There will be some people that apply negative potential energy to things. But we can, as long as we have a consistent thing, we're going to be fine. But so here, I'm going to consider this to be the datum for this block, and I'm going to consider the datum for this to be for this block. I'm totally fine to have 2 different datums. We could also have one that's below that they share and just measure it up to there. Some arbitrary, we could just pick a number if we wanted to.
For the global one, though, because we don't, I mean, in this case, all you know is their changes in height. You don't know where they initially are, so it may be tricky to use a global one.
Yeah, well, I'm just saying as a general idea, right? That being because it seems like you might not come to the conclusion, oh, each one has its own datum. Well, yeah, but it's actually a global datum if you put this box in. I didn't mean to confuse it. Maybe that confused them. So anyway, at PE1, this guy has potential energy. This guy doesn't yet have potential energy based on the way that we drew the datum right here, right? So that, in keeping with this way, that'll make it, that's the technique to keep it so that it's positive potential energy. So this is going to be M, and we never call this thing, I guess this is A, and this is B. So we go M, A, G, and then we go delta Y of A. Here we notice that this is going to be, what's the angle that we say, as you mentioned, it's a triangle. I think that's where you're going with. And that we're having it right here. So that's going to be this 2 times the sine of 60 degrees, right? So I'm not sure they did it here. Yeah, they did. Okay. Actually, and on here, by the way, my former coworker, did make it negative potential energy. I hate negative potential energy. But so we will just try to figure out what this in-between number is ourselves. So that's going to be 29.81, yeah. And then it's going to be 2 times the sine of 60 degrees. Somebody solve that for me, please. Appreciate it, thanks. I like to give them on my little used little hats. Make it a little exciting. Cy tried to call me. He stopped by and asked me, he said, hey, stop by my office. I stopped by his office, it wasn't there. I tried. Anyway. What'd you say?
339.82.
339?
Yeah.
0.8?
0.82.
I only need 466. I appreciate your additional enthusiasm for this.
466.
And these are Newton meters, right? That's the units. Right? It could be joules. There's also remarkable joules, but that makes me think I'm in thermo class, and I just want to avoid that. All right, so we got what kind of external? I think this is the thought process that we're going through for as we're picking these apart. So okay, so we took care of. Now we get to this part of the. What do we want? What's the external stuff taking place here? Friction, yeah. And what do we use for the like maybe the variables or the equation for this friction? We would say that it's the friction force, right, times the amount of motion. Usually we go delta, and you got to be careful. We go x right here. And in this case, it's going to be this delta x. But what do we think about this? We should keep in mind really quickly here. We should remember right here about the friction energy. It's positive or negative? It's negative. You can have two different reasons to be negative, right? You can think of it in two different ways. One, the friction force is going that way, but the motion is going this way. So they're opposite from each other. And remember that actual equation for this is the integral of F. Well, no, I think it's actually getting this backwards here. Is it F? Yeah, it's F dotted dr. So the dot product of this, when you dot product something that's 180 degrees from each other, it becomes negative, right? But you could also say that it's energy being removed, right? So that's another reason to make it negative, that we had, here's the energy before, here's the energy after, and this is something happening to it. Yeah, so this is like the external stuff that's taking place right here. So this is like thermal class, I guess. So we got negative taking place. And to be able to get that friction force, we really should be good citizens. And what did Neil tell us to do? Anybody in that? I know I had a couple of you when I subbed for Dr. Orlock, right? Neil Armstrong, he told us to make a free body diagram. Because Neil, he's been to the moon. Have you been to the moon? No, you haven't been. I don't think anybody has. But Neil's been to the moon, so you got to do what Neil says, right? Neil knows. We have the force right here of the tension, and we have the weight M-A-G, and we have our F, and we know the friction is going this a ways right here. And we're going to need this in a second, by the way. We're going to need this for part B of this thing. So, and we know that it's going to be accelerating here, by the way. But we don't necessarily need this part for what we're doing right here, but we will need it in a bit, so it doesn't hurt. And doing the sum of the forces in the x prime direction here, that's going to be positive here, is equal to, I don't want x prime, sorry. I want y prime to start with. Later on, I will want, no, I don't, because I don't want to use Newton's second law. I'm not going to use Newton's second law for this, so I just lied. I promised I would never lie to you, but I just did. Y prime. But it's not accelerating in the y prime direction, so it's going to equal 0. So we take and say that and this angle right there is 60 degrees. So we take negative MAG cosine of our 60 degrees, and we have positive Fn is equal to 0. So Fn was equal to, did we work the thing out, or did she, no, she left it as variables because she liked to do that. So it was 29.81 cosine of 60 degrees. Anybody? Bueller? No? Oh, you're too good, man. Math. Try it out sometime. Yeah, no, do this one again. 0.2 times 98.1. I know you can do it. 0.2, I can't. Get 19.62 newtons right there, right? So we have negative 19.62, and it's going to be moving 2 meters down the slope. So that's negative 39.24 newton meters. And then what are we looking for anyway? I'm trying to remember. We want to find the velocity of B. Okay, when this happens. So we get this kinetic energy at 2 as we're marching through this thing. It's going to be, I heard somebody say 1/2 mv squared, so I know you know. MAVA2 squared plus 1/2 MVVB2 squared. One thing that we could do as part of this right here, we recognize that this is not part of the problem. It happens to be just hanging out right here, just not doing anything. We could do a dependent motion problem, but this is a pretty easy dependent motion problem. We can say that VA is equal to each other. And what we were asked for was for the velocity of B. So we might as well like substitute that one in there. So we can say that it's going to be 1/2, I might leave it this way here, 20 VB2 squared plus 1/2, and this is 10, right? So VB2 squared. So I just lied. So what is that going to end up having to be? 15? Yeah, 15. This is film. It's not film. There's no film. It's not film. And then lastly, we got PE2, which is now going to be the change of only him, right? So it's MBG delta YB, which is going to be 10, 9.81, and times 2. So that's going to be, I think it's going to be a number that's really close to this. This is going to be 196.2, right? 10 times 9.81 equals times 2 equals 196.2. Now, where Dr. Garcia and I disagreed on things was she liked to plug numbers in at the end. I really like this because this gives me information that she doesn't have. I know where the contributions of each of the parts are, right? So as I go through here, I go, oh, there's 0 plus 339.8 potential energy. That's really the driver of the thing. That's the thing that's making it go. But then we have to subtract out our 39.24, and that's going to end up giving us that 15 times our VB2 squared, but we have some left. We have some trade-off between our potential energy. Well, where did that potential energy go? Some of it got robbed over here. Some of it got moved over. The other guy picked it up where this guy dropped it. This guy picked it up, and then the rest became the kinetic energy onto the thing. So we end up with VB2 is going to be equal to 2.64 meters per second. They did ask for velocity, even though it looks like we took our glasses off. So you might want to put this right here and put that right there to give it a complete answer. How are we doing on time? Okay, so part 2 of the thing asks for the tension in the cord. All right, so there's a couple things, 2 different ways that we can approach this. We're probably tempted to use Newton's second law, but I think the problem, no, not this time. A lot of times we said you must use work energy. All right, a lot of times I will say that. You must use work energy. So how would we go about trying to find the tension in this using work energy?
Force does work.
The force does work, so the tension in the cable does work, doesn't it? The only way that you can ever find the tension in something is to cut and look inside, right? So you have to cut the cable and then see what's going on. So what we want to do is we want to look at one of these blocks. We can't look at both of them. Here, one of the nice things about work energy is you could keep a system together. Right? And what we needed to do when we had those other blocks and using Newton's second law, we had to separate them by equations. They were connected to each other by having the tension in the rope. But here, we need to find that tension. The only way that we can is to separate it. I would tell you the easiest way to do this is to use block B, but we could use block A to find that tension. So there's multiple things. But what we could do is, I'll draw this over to the side right here. We have the force of the tension right here onto B, right? It also has weight going on here, but we don't need to draw that. In our potential energy, our energy diagrams, we often will only draw like these 2 states. Like here's state 1 and here's state 2. This remains our datum. So what we found here is if we were going to write out again this, but this right here is only going to be for that block. And I probably wanted some of those numbers, that's okay. So what I could say here is my kinetic energy at the beginning is 0 again. My potential energy at the beginning of this for just B is also equal to 0 because that's the datum. The work that's going to be applied now is going to be this force of the tension times the distance it moves in there. And they're in agreement with each other, so that's positive. It's also energy that's being added to it. That energy is coming from A. But it's external when we've written it as this thing by itself. Right? And so then when we get to the end right here, it's going to have some kinetic energy. It's going to be 1/2 mBv/B2 squared. And we just found what that was, 2.64. We probably should have another sig fig in there, but we'll leave it alone right here. And we go 2.64 squared times 34.85. Oh, and by the way, this is going to be FT times 2. And then our potential energy, we actually had that written out before, right? That was going to be right here at the state 2 right here. It's going to be our MBG delta Y B, or 10, 9.812. Was that the 196 or something? Anybody remember? I erased it. Is that right? Thank you. So writing this out over here, we have 0 plus 0 plus F of the tension times 2 is going to be equal to 34.85 plus 196.2. And the tension should come out to 115 newtons. Could we have done this with Newton's second law? Yes. Because none of the forces vary with time. We're able, and we know the velocity, so we're going to have so we are going to be able to find an acceleration using kinematics, right? We could use the constant acceleration equations to be able to get out what is the acceleration of block B, because we have a velocity and another time. It's because this time doesn't change. We could theoretically use it if there was a spring involved, but it would be a lot more difficult, because then if a spring is involved in one of these systems right here, that force varies with position, therefore it varies with time. So it would be a more difficult thing. So it's not a constant acceleration problem when it's not a constant force problem. When the force changes with time, the acceleration changes with time. But here, none of the forces change. They're the same at any given moment. Is that clear? It's a pretty good problem. I like the second part right here, because it gives you kind of like, oh, there's another external force taking place. Take a look at, we got like another 10 minutes or, the oblique impact problem. Usually we don't do two directions having two separate velocities for an oblique impact problem. And that is the last topic in the last class that we had before the exam. But it's still a fair game. The one I have right up here is a regular impulse and momentum problem. So I alluded to it, so you might think about using this one, trying this one out as well. That it has a velocity before and a velocity after, and has some type of, there's a gun firing off there. Of course, this was done at the Coast Guard Academy, so they have a little Coast Guard boat on it. But I was thinking about this one right here when I was talking about an oblique impact problem. Does anybody watch curling? Oh, this is the curling team. You know what curling is? Did you ever see that with the broom?
Yeah.
That's nuts.
It's crazy.
I don't even know why that even works.
Well,
Why does the thing move? Because they're brushing in front of it.
when they brush the ice, it melts the ice a little bit, so it changes the coefficient of friction. So that's how they can steer.
Are you serious?
Where it goes.
Is that really
So
why
they'll do it on one side, like one half of the ball, so they can steer where it goes to. It's cool. It's good.
Have you tried it?
I've never tried it. No. My uncle's on the curling team though.
Really?
Yeah, he loves it.
Claim to fame.
From the
My
West.
uncle's
Yeah.
could have been. Man, that's awesome. In this guy right here, we have velocity of 4 feet per second of A, and it's striking this guy along an arrangement here where this is 30 degrees. And the important thing to do when doing one of these is to set up that normal and tangential axis onto the thing. So, and it'd be nice if I would draw the same picture close. That would be good. I'm all like upset about it. I want to go with this curling now. Now that I know that, I'm upset that I didn't know. Kaboom happens right here. This guy has a MAVA1, and then afterwards, all right, so what we notice into here, it's a good time to break it up into components, that it has an MAVA1, call this tangential because we call, let's go, this is the normal direction and that's the tangential direction. And this has the MAVA1 normal right here. So we might even consider like writing that out like right away. That's something that's not difficult to do. That's just the VA1 times, and this is, let's see, did I get the angles right? Yeah, it's going to be the 30 degrees right there. So this is going to be the sine of 30 degrees. Is that true? 4 times the sine of 30 degrees. Is the sine of 30 degrees 0.5? Or is it the 0.8 times the 0.5? Okay, so I could do that, right? 2 VA1 normal. So you have 4 times the cosine of 30 degrees, and that's the 0.866 one, right? And she never does this for me. She never gives me the in-between numbers. I miss her. She was right across the hall from me, and we were like, we'd have our own intercom system. We'd just yell across the hall at each other. Why'd you give her number 2? I haven't done it yet. Hurry up! She's mean to me all the time, too. She's like my kid sister. I think she thought I was the younger of the 2. So 1.7 short attention span, 3.2. I miss her son, Skyven. Kind of weird, man. He'd come in all the time. Hey, Ted, what are you doing? He was like 3 years old. Actually, I think he was probably near 5 by the time. I guess we. Yeah. I just remember as a 3-year-old because he was going. He'd always go. I had Legos and stuff in my office, so he'd always come in. He'd always be playing with the toy. I had a lot of toys in my office, so still do. And I don't have any little kids coming by my office anymore. Yeah, but I also had other things, and he picked up a razor blade one time. This big, nice cutting knife, and I'm like looking over there. Oh my god! Like, I'm more responsible than this, I swear, with my own kids at least. So this guy right here, we know that this is going to be the same afterwards, right? So this is the MAVA2 right here. In the tangential direction, we know that's going to be the same right here. VA2 tangential right here. But we don't necessarily know what direction. These are the same weights, right? They're the same masses. They didn't even tell us that, no, each one weighs 40 pounds. They did say. Each one of these weighs 40 pounds. Quite often you'll see, though, when you have stuff that has the same weight, the masses will cancel out. But triple check that as you're going through the thing. Right? It's a good practice. Blue decided to go down for the count. I have to buy some new markers. So when this happens, we don't know whether for sure it's going to bounce backwards. Right here. So you got to be careful with the signs in here. If you don't know, always go positive. So MA, VA2 in the normal direction. And now this one only can have stuff in the normal direction. So that's going to be MB, VB2 normal direction. And so when we write out the impulse and momentum from this, we'll do this in the n direction. So we'll say that MAVA1N, right? And there's nothing going on in the n direction there, so that's fine. It's going to be E, and the impulse is 0, so maybe it's a space holder. We'll put a 0 into here because they're equal and opposite to each other. And it's part of that. And it's equal to that MAVA2N plus our MBVB2N. But like we said, we noticed that they weigh the same thing, so those can all be canceled out. So we can make that decision at this point right here, but to recognize the thing. So what we're left with is 1.732. You got that right? Is going to be equal to VA2N plus VB2N. So that's one equation. We need another equation because we have two unknowns right here. So we apply the coefficient of restitution. So this is the negative vel-rel after divided by the rel after, before. Wow. Very late, very tired. We on our equation sheet there, it is written out in the I think it looks like this right here. V, probably B, I think I use primes, but I don't like primes anymore. I'm trying to wean myself off of the primes. I think it's a weird way to write the thing. But I think it's written out this way on the equation sheet. Just to be aware. Be careful with this. Make sure we swap the ones over. And it's written out with the ends in there to remind you that it's all about the end right here. So this is the same thing as that what we had said for the other one. So what we could say is the VB2N minus the VA2N is equal to our coefficient of restitution, which we decided was 0.6 times our VA1, which is 1.732. And this becomes our second equation. And from these two things, we can separate them out. And what we end up finding that, so she leaves things as square roots. She has 4 times the square root of 3 as one of the answers to this right here. Because she never uses the cosines and the cosines of things. She like goes, well, that's really the square root of 3 over 2, right? I think the cosine of 30 is she just remembers that. Oh, no, I can do it. No, I won't do it. Just won't do it. And so anyway, what we end up with is we get the components right here. I'm getting really tired. I don't know. I'm going to get lazy. Times 0.6 equals. So this ends up being equal to 1.039. So the VB2N minus the VA2N. So I might solve this one first right here. So I'll go VB2N is equal to VA2N plus 1.039. And I shove him back over into here. And I go 1.732 is equal to VA2N plus VA2N. Did I do this wrong? Seems like it's too easy. So VA2N is going to be equal to, I subtract any. I subtract instead. Subtract 1.7. So, and then I divide by 2. So it's equal to 0.3464 feet per second. And then, which one do I want to use? I just had this right here. So I add these two together, right? I add that to that. And it came up to a positive number, right? So it did keep, I was correct. It did keep on going. It just slowed down, right? I think if the mass ratios came out there would be like a bigger chance that, like if this was a bigger mass than that one, it would have gone not backwards. So the VB2 and would have been so this goes 1.385 feet per second. Now to actually get the final answer is a little bit of a pain. You're going to be kind of careful right here. You could be, you could, well, we do know that, let's see, I'm going to double check the answers. Actually, I must have messed something up along the way. I messed something up along the way. I got a wrong value in here somewhere. Darn it. What did I do wrong? I can't tell from here, and I'm really tired. There's an error here. Because this right here should have somehow been 2.77.
That's exactly what I said you
I wonder how. What do I do wrong?
Did you get the same answer for VA2?
Well, she doesn't have the in-between thing here. The next step that we have to do is we have to combine these together to get, she left them like in partially done thing. But this is something that we want to be careful with right here, is we want to find what the VA2 is going to be, is the square root of those two parts. And then we're going to find an angle from the inverse tangent. But remember, of the two parts, but remember that those components are based on this coordinate system. So you need to either add or subtract, depending on what quadrant that you end up with this answer, to be able to get it to be a correct value. All right? And I think in this case you actually had to subtract it, because it ends up coming down, and the answer, according to this, is that it's going to be 2.12 feet per second, 40.9 degrees for VA2. And I don't know what happened to this other one, but I was trying to be consistent. I need to end because I really just worn out. My third, I did 3 today. This is crazy. This is stupid. I did 3 review sessions.
What did you do before on April 2nd?
I did 401, my mechanisms class. I had in their first exam. Because they said, we want a review session. I've had some of them for, this would be my 3rd time having them as students. And so I jokingly said that I fed the cat, so now I own the cat, right? Because I gave them some review session, now I owe them a review session. Thank you. Sorry I didn't use you more. Oh, you're fine. That's good. I gotta figure a way to do more stuff where we have more interaction. Oh, hey. Stop now. Hey.